Okay, and in this particular spirit there is the so-called double layer potential. And for the double layer potential you make the following ansatz. Ansatz is one of those German words that even made it into English daily use, at least for mathematicians. So just like here, where you take a linear combination with unknown coefficients of translates of your fundamental solution, now you take an integral, and instead of the unknown little alphas you get an unknown function, little f, and then here's your kernel k of x and let's say y, like here. And now little y is running around all these points of translation, but in this case this is not just a finite set. In this case we use the boundary of our set omega for these translates y here, and so f is now a function on the whole boundary of omega. Okay, for our integral we cannot simply write dy. We have to take the surface element here because y is running around the boundary, which in 3D is a proper two-dimensional surface. So let me denote the surface element by ds at point y. So y is one of these points that I'm running around on the boundary of omega. And what you get here will still perfectly solve your Laplacian equation, because it's just a slightly heavier version of that guy here with infinitely many instead of finitely many points of translation. And in fact the name for this is single layer potential. But for some reason we want the double layer potential, and for the double layer potential you do one more slightly crazy thing. You take the derivative of your kernel function into the direction of the normal vector at point y. So the normal vector at point y would be this here. You always take the outward normal, so it's looking to the outside, and normal vector means that it is orthogonal to the boundary or to the tangent that you can put on the boundary at this point. So in particular you're assuming that your boundary d omega is sufficiently smooth that you can even talk about tangents and normals. Okay, and now this is just a directional derivative into this particular direction that is normalized, so this is supposed to have length 1. And the amazing thing is that even after doing this, you still get a solution of Laplace's equation. So you can see that this thing is quite robust. You can do lots of things. And you can compute this partial derivative or this directional derivative explicitly and get the following, where this expression x minus y here comes from the gradient of the function k, and the scalar product with n of y comes from how you compute directional derivatives. Maybe you have to recall that one from your analysis too. Okay, and the minus 1 over 4 pi in front was already here in k. Now you can plug in every x from R3, and you would expect me to say that it's not allowed to plug in points from the boundary like we did here, because that's where the singularities sit. In fact, one can make sense out of this integral as a so-called singular integral, even for points on the boundary. So we do not have to exclude them. It's just funny things are happening when you plug in x as a boundary point. We will come to this in a bit. Okay, so just like these little alphas here were unknown, now our function f is the unknown function, and it's a function on the boundary only, because that's where little y is running around, and it is a continuous function. And often people call it the density function, because somehow these little alphas give you weights. They tell you how heavy or how important the shift to that particular xj is, and well, somehow this is playing the same role. Okay, like I said, so this function u will be subject to Laplace's equation, well, let's say in omega, so properly inside the boundary, and also in the outside, but not so much on the boundary, because like I said, it's doing funny things on the boundary. And one of these funny things is the following. When you come from the inside and move towards a boundary point, let's call it x0, then your function u has the following limit. The limit is u at the boundary point, x0. And now here comes the funny bit. The story is not over yet. You add something, and that something is 1/2 of the density function f at that boundary point. So if this term wouldn't be here, then we had a perfectly continuous function. You move towards that boundary point, and your function value converges to that value, but you get this perturbation here. So you get a jump, and the density function, or half of the density function, tells you how much you're jumping. Okay, and in our case, looking back to the boundary value problem, we want the limit as u goes to your boundary to be given by this function g on the boundary. So now function g enters the scene, and this is here. Okay, so if you follow your function u nice and smoothly towards the boundary without any jumps, because you're looking for a continuous function u, then at the boundary point you want to see this behavior, and this g is given, and this f is still unknown, and this u is given in terms of f by our double layer potential ansatz here. Maybe let me label that. So let's spell this out again. G of x0 equals, now we have to copy the u of x0 expression again from our double layer potential ansatz. And the only point to be careful here is that we are evaluating u not at any point x, but at this boundary point x0. So we have to put little zeros here and here. Okay, so this. And now let's not forget about this part here. Okay, to get rid of this half here, you would multiply everything by 2. And then you simplify here. Okay, and typically you would get that thing in front of here. Well, you can obviously exchange the order of summation. And then at some point you get tired of this clumsy expression here. So you abbreviate this by integral operator, usually denoted by capital K, applied to the function f, because it all depends on f, obviously. And then you get another function, and that function is evaluated at the point 0. And it's easy to check that this is a linear operator, right? So if you multiply this function f here by a little alpha, then this little alpha can come out, of course. Or if you do this for one function f and then for another function f, you can add your f's first and then plug in, or you compute the integrals separately and then add up. So you obviously have linearity. Okay, so this is a linear integral operator. And I guess one of the reasons why people like to call that operator k is because it turns out it's a compact operator. Okay, and with this notation of our integral operator k, we can rewrite in a nice and tidy way what this long equation is saying here. So the equation says that 2 times g of x0 is f of x0 minus k of f at x0, and that's supposed to hold for all points x0 on the boundary of omega. Or in short, the following equation of functions holds on the boundary. Okay, so 2g equals f minus kf. And now we're just 2 steps away from a nice and tidy ax equals b. First step is to say there's the identity operator sitting here, and then to factor this out. And the final step is to denote this I minus k by your a. Okay, of course we could also call this b, but let's not be silly here. Right. So clearly a is a bounded linear operator, being the identity, which is bounded, minus a compact operator, which is bounded. And it's one of those operators that I announced a couple of weeks ago, where I said identity plus or minus a compact operator often appears in applications and is particularly nice to approximate. Integral equations where the operators of the form I minus compact operator are often called Fredholm integral equations of the second kind. And you would call them of the first kind if the identity wouldn't be here, but we all know that this is much nastier. We spoke about this problems with compact operators and invertibility and ill-post problems and so on. Okay, so the probably last thing that needs to be said here is how you would approximate that. And like I said earlier, there's no need to approximate the identity. We can clearly deal with that. But what you approximate is your compact operator k. You would approximate that by a sequence of compact, possibly finite rank operators kn. And there's a very good choice, if you do your approximation right, that this will be uniform convergence. And then, if you call this result an, that will be uniform convergence. And then we all know the world is great, because we had this theorem at the very beginning of chapter 3, which says in the case of uniform convergence, then invertibility of A already makes sure everything will be fine. So this sequence will be stable, it will be applicable. And of course, what is typically done to define these approximations kn is to take your integral here and discretize that in a nice way. Okay, by summations and finite expressions. Maybe it's not so important here to memorize this expression, Fredholm integral equation of the second kind, but it's probably more useful to, I mean, it's correct, but maybe it's even more important to remember that this is what people call a boundary integral equation. And clearly what boundary is coming from the fact that this is only an equation on the boundary of omega anymore, and of course, it involves an integral operator. Okay, and speaking about that, let me mention one other benefit of this method. So one benefit was mentioned already at the very beginning. You turn an unbounded operator equation into a bounded operator equation, which is typically a good idea, especially when you're taking this course here. But there is a second, even more convincing reason why this might be a good idea. For finite element methods or finite difference methods, I said it before, you would discretize the 3D space around your omega, cut it into small pieces, cubes, pyramids, whatever, and gets lots of elements, huge systems, because it's 3D. Here, your equation is only taking place on the boundary, and this boundary is so much smaller than the whole body omega, which is a 3D body. So if you compare the size of a 3D object to its boundary, then of course the boundary is a lot smaller. So it takes a lot less points to discretize that boundary, and that's why it takes a lot smaller systems to write down these equations here. So these are much smaller systems, and they still do a great job in approximating this problem, and thereby in the end, when you solve that, you get your density function f, and if you plug that into your double layer potential ansatz, then you get your unknown function u. Okay, let's write that down. Okay, excellent. Just before reaching the finish line, I just noticed that I made a little copy mistake here. So of course the double layer potential is an integral over the boundary of your set omega. We introduced it like that, and we've been saying that this function lives on the boundary, and this is the surface element. And then I forgot to write little d in front of this omega here. Of course, you need to put that in order for things to make sense. And of course, that's why we call it a boundary integral. Sorry about that. Now I think we can draw the finish line here.